Effects of program/erase cycling. Flash memory p-cycling causes damage to the tunnel oxide of floating gate transistors in the form of charge trapping in the oxide and interface states, which directly results in threshold voltage shift and fluctuation and hence gradually degrades memory device noise margin. Major distortion sources include electrons capture and emission events at charge trap sites near the interface developed over p-cycling directly result in memory cell threshold voltage fluctuation, which is referred to as random telegraph noise, RTN. Interface trap recovery and electron detrapping gradually reduce memory cell threshold voltage, leading to the data retention limitation. RTN causes random fluctuation of memory cell threshold voltage, where the fluctuation magnitude is subject to exponential decay. Hence, we can model the probability density function of RTN-induced threshold voltage fluctuation as a symmetric exponential function. Let note the p-cycling number scales within an approximate power law fashion, i.e., is approximately proportional to threshold voltage reduction due to interface trap recovery and electron detrapping can be approximately modeled as a Gaussian distribution. Both in scale with NAND in approximate power law fashion, and scale with the retention time in a logarithmic fashion. Moreover, the significance of threshold voltage reduction induced by interface trap recovery and electron detrapping is also proportional to the initial threshold voltage magnitude, i.e., the higher the initial threshold voltage is, the faster the interface trap recovery and electron detrapping occur and hence the larger threshold voltage reduction will be. Cell-to-cell interference. In NAND flash memory, the threshold voltage shift of one floating gate transistor can influence the threshold voltage of its adjacent floating gate transistors through parasitic capacitance coupling effect, i.e. one float gate voltage is coupled by the floating gate changes of the adjacent cells via parasitic capacitors. This is referred to as cell-to-cell interference. As technology scales down, this has been well recognized as one of major noise sources in NAND flash memory. Threshold voltage shift of a victim cell caused by cell-to-cell interference can be estimated as where represents the threshold voltage shift of one interfering cell which is programmed after the victim cell, and the coupling ratio is defined as where is the parasitic capacitance between the interfering cell and the victim cell, and is the total capacitance of the victim cell. Cell-to-cell interference significance is affected by NAND flash memory bit line structure. In current design practice, there are two different bit line structures, including conventional even/odd bit line structure and emerging all bit line structure. In even/odd bit line structure, memory cells on one word line are alternatively connected to even and odd bit lines and even cells are programmed ahead of odd cells in the same word line. Therefore, an even cell is mainly interfered by 5 neighboring cells and an odd cell is interfered by only 3 neighboring cells, as shown in figure 3. Therefore, even cells and odd cells experience largely different amount of cell-to-cell interference. Cells in all bit line structure suffers less cell-to-cell interference than even cells in odd/even structure, and the all bit line structure can effectively support high-speed current sensing to improve the memory read and verify speed. Therefore, throughout the remainder of this paper, we mainly consider NAND flash memory with the all bit line structure. Finally, we note that the design methods presented in this work are also applicable when odd/even structure is being used.